Hello, everyone, and welcome to today's Alkene Reactions live session. We are just about ready to begin. First, quickly looking at the comments. Noelle, it is good to see you, and I saw your message that this is perfect timing, so that's excellent. Nicole, elimination quiz on Friday, substitution elimination on the 21st. Oh my goodness, how are finals just around the corner? Noelle's final is December 10th. That's a month away. Wow. I've been fine ever since we got to alkenes. Excellent. Unless you mean that sarcastically. I'm not sure what that emoji means. Maryland exam 3 November. Oh, exam 3 November 25th. I was reading that as November 3rd and I got confused. We have another Maryland, Daniela from New York. Where in New York are you? I am in Long Island, so could be neighbors. Lucia from Chicago. And I see exam on Monday, exam tomorrow. Lots of requests for the notes. Excellent. So I am a little bit behind in getting ready today. My son went down early and I thought, great, I have plenty of time. Somehow plenty of time turned into not enough time. And so here we are, where I'm scrambling a little bit. But if you put live notes in the comments, I'll send you the link so you can download all of the notes and everything that you see me writing today. This is going to let you focus on the concepts, the reactions, and just everything that we are going to do. So let me pull up my notes. All right, let's jump in with what I often draw jokingly at the start of the semester, but I think this is a really good time to come back to it. All right, let me know if your heart rate is starting to go up a little bit, because here we are. The thing with alkene reactions is that when you're learning it in lecture, you're given a simple molecule. You're told, here is what's going on, here's the reagents, and it feels pretty good. It looks pretty straightforward. Then you get to your homework and the molecule looks a little bit different. You have a couple more things to consider, but it still feels kind of doable. And then you get to your exam and you're shown this. Let me know in the comments if you think I'm exaggerating at all, or if you have actually seen this happening. When it comes to any reaction in organic chemistry, but especially with alkenes, if you can look at the molecule and recognize, this is what I know about the reaction. This happens, this happens, this happens. Everything else is just extra. It's just there to scare you. Because I see you're not exaggerating, spot on, spot on. I have seen this before, a lot of confirmation. So what I want to focus on today is not teach you all the alkene reactions, because I've got plenty of videos and a cheat sheet for that. What I want to show you is how you can learn this reaction, how to recognize what is going on, and then no matter which of these versions you see on your exams, you will know exactly what to do because you get it, because it's inherently logical for you. So let's jump in first with just a quick review of the pi bond itself. Alkene reactions have a functional group called an alkene. And even though this is drawn just as a carbon with 2 lines to another carbon, that double bond, those 2 bonds are very, very different from each other. If I take the 2 carbon atoms and I draw them next to each other, you have a sigma bond. That's the single bond, that first bond, where the 2 atoms are connected to each other. That is that strong single bond in the middle. Then you have the p orbitals that sit both on top. Whoops, it should be disconnected. So it's kind of like this, on top and on bottom. And you have a p orbital from the other carbon also top and bottom. And when those p orbitals overlap, that's where you form that pi bond. So it's not 2 pi bonds. It's the top half and the bottom half. It can go in the X, Y, or Z plane. I just happen to draw it like this. But what I want you to recognize is that while these electrons here, the sigma single bond, is sitting there very tightly holding on, the two carbons are very tightly holding on to each other. The pi bond sits very high and very low on the molecule, so it's not directly attached. Almost think of this like walking a very well-trained dog that is on a short leash, stands right beside the person, and this one would be more like my in-law's dog. My in-dog. we call her Aunt Gracie. So to my son, she is Aunt Gracie. She's a 3-year-old mini schnauzer, and that thing, you give her a 12-foot leash and she is all over the place. She's ahead of you, she's behind you, she's crossing in front of you, all over the place. Yes, she's attached because that leash is being held very carefully, but she will take the full rein of that leash and stop for everything. That is how the electrons, the pi bond electrons, are behaving, and that is what is going to drive all of the reactivity of these alkene reactions. To understand from an organic chemistry perspective, we want to look at the two players within most of the reactions, and I'll show you which ones are not, and that is the nucleophile and the electrophile. You will see these terms over and over in organic chemistry, and it's very important that you inherently understand rather than just memorize what it is that you're looking at. I just realized I jumped in without an introduction, so welcome everyone. We are going to cover, well, I kind of told you already what we're going to cover today, but don't worry about copying everything down. Just put live notes in the comments and I will send you a PDF of everything that you see me writing today so that you can focus on learning and understanding and have the notes taken for you. Yes, even if you're watching the recording, my assistant will go through the comments and make sure you have the link. So going back to nucleophile and electrophile, what we have in the word here, nucleo is like nucleus, and phile, I don't know why I'm writing phile again, phile means loving. A nucleophile is nucleus loving, and if you think about the charge of a nucleus that has all those protons, the nucleus is positive, therefore something that is loving of a nucleophile loves the positive. We can call it positive loving or positive seeking. What type of atom or molecule is excited to reach out to or seek a positive? It's going to be something negative or partially negative. So you will see me write the nucleophile as Nu ... like that. Nu for nucleophile and the ... to show the two electrons because they tend to move as a pair, except in the radical chapter, which is completely different. And then for the electrophile, same idea. We have electrophile, which is electron loving. And electron loving is technically negative seeking, but the positives never reach out to the negative. The positives attract the negative to get attacked. And so something electron loving would be positive or partially positive. And that is why and how it attracts the electrophile. So if I had to sum up the alkene chapter mechanism in one reaction, in one mechanism, or really a good chunk of organic chemistry, it is very simple. We have a nucleophile, we have electrophile. The nucleophile has those electrons that are looking for positive or partially positive. The electrophile is positive or partially positive. It gets attacked, and we get our intermediate, or we get the product. This is what we're looking at for most of the alkene chapter. And so before we jump into the reactions for the patterns and the shortcuts, there's a few more things we have to look at. The next thing I want to look at is syn versus anti-addition, because when you're given a problem, showing the product is not enough. You have to show how the groups add in relation to the other groups and to relation to what was already there. So let's take a quick look at, well, if I show you just a pi bond, it won't matter. That's why professors like to use rings. Well, I think they like to use rings to scare you, but a ring makes it very obvious what is going on because with a ring, you have no rotation. Let me actually show you both so you see what I mean. If I have a pi bond and I do some kind of reaction where the pi bond breaks, and I get two things adding across the pi bond. We'll add A. Why do I keep going to green today? Let's mix up the colors. We'll have A and B adding across the pi bond. If let me draw two skeletons first. One quick tip for problems where you don't need a mechanism, Always draw your skeleton first, then add to it. If I add A and B across the pi bond, I can put A on a wedge and B on a wedge, or A on a dash and B on a dash. Or I can put them opposite, A on a wedge, B on dashes, or the reverse. I'm not going to draw all 4 options here. And in this situation over here, the molecule can rotate. So actually, in this case, they would be enantiomers of each other. If I flipped it, rotating wouldn't help. But sometimes the rotation can make a difference, or won't make a difference, because you would have an achiral atom. But on a ring, it's very, very obvious, because a ring cannot rotate. So if I put A and B together, or I put A and B, why am I drawing so small? I don't know. Or if I draw A and B opposite, and these are just 2 options, I could have put both of these on dashes, and I could have flipped these 2. These are the 2 types of additions that we can get when you have something adding to one carbon of the pi bond, something adding to the other. If they add together to the same face of the pi bond, either both wedges coming out of the page or both dashes going into the page, this is called syn addition. Syn, same side, SS, syn, same side. And when they go opposite, they are anti to each other. This is called anti-addition. First, let me know if this is clear, because this is going to be very, very critical. And the second thing that we have to look at, and this one I'm going to challenge you to tell me the simplest definition for it. Markovnikov's rule plays a very big role. Markovnikov. I cannot spell his name unless I say it. Markovnikov, that is so many letters. We are going to call this Mark's rule for the duration of this session because of my sanity, and I don't want to write his name so many times. What is Markovnikov's rule, and how does it impact what we're going to look at with alkene reactions? As you're thinking about it, I'm going to draw out a simple mechanism, not a mechanism, a simple reaction, so that we can take a look and show you the 2 potential products, this time without stereochemistry. I'm just going to focus on where they add. So this one focused on stereochemistry. This one focuses on regioselectivity, what region is selected. If I add A and B across the pi bond, I can add A and B, or I can add B and A. Markovnikov's rule tells us which one is going to form in each situation. And there are a couple of different ways that you may have learned it. I have heard that the hydrogen goes to the less substituted, the incoming nucleophile goes to the more substituted, the hydrogen rich get hydrogen richer. Those are all outcomes. Those are all, it happens, it's a fact you memorized. I don't like that. I am more interested in why it's happening, because then you will be able to intuitively come up with a product. Noel, the most stable product, yes, that is what we're looking for. But I want to clarify, it's not the most stable product, it's the most stable intermediate. If you have to do something and the process of doing it is hard and you don't like it, you're probably not going to do it. And if you are going to do it, you're going to be very slow, you're going to delay, you're going to stall. And so an intermediate for a reaction that is not stable is going to be very slow and therefore less likely to form. But if the intermediate is stable, Lucia, absolutely, the most stable carbocation is going to be the fastest to form because it is happy with where it's going. It's not afraid, and therefore it doesn't stall. So instead of thinking about hydrogens and nucleophiles, which we'll definitely look at with the shortcuts, I want to look at it from the perspective of the stability of the intermediate. As a quick reminder, I don't think I gave it to you for homework today, but I know I gave it to you for homework for the substitution elimination sessions. Carbocation stability is what we're looking at for these intermediates. And this is going to be critical to doing the shortcuts. So that's why I'm taking the time to spend on it. A carbocation is a carbon that has a positive charge. And even though we're calling it stability, it's not stable. A charge is a burden, and the atoms do not want to carry that charge. But if they have moral support, if they have a cheering squad, if they have someone around them helping them, either physically helping with resonance or just there from having multiple groups nearby for what I call moral support, then the carbocation is going to be more stable. So the least stable is just a methyl carbocation, and in organic chemistry, just assume this doesn't happen. Slightly more stable than a methyl carbocation is a primary carbocation. For the sake of organic chemistry 1, this is not going to happen. I say for the sake of because in organic chemistry 2, you have some really, really extreme reactions in the EAS chapter, electrophilic aromatic substitution. You are going to see this, but those are extreme conditions. So we'll do a double to show that now the next ones will happen. A secondary carbocation has support from both sides. That is why it's stable. A tertiary carbocation is surrounded by support, making it the most stable. And this is just moral support. No one is physically helping. More stable than that is, of course, resonance. And so if you have a primary allylic carbocation, in this case, the primary can form because the charge is being shared by 2 different atoms. I can show the resonance contributor here like this. And I'm showing primary, but you can have secondary and tertiary. And even more stable than an allylic carbocation is a benzylic carbocation because there is so much more resonance there. I went into this in detail in the resonance session that I did. So if you want to review on this, if you're not crystal clear, make sure you go back and review. But notice that we can have 1, 2, 3, making this very stable. It is my understanding that a primary benzylic carbocation is as stable as a tertiary no resonance carbocation. And obviously, if you add substituents here, this becomes even more stable. So what does this have to do with Markovnikov's rule? First, questions. Not all reactions for carbocations exactly. And that is the key to knowing Markovnikov or anti-Markovnikov. If there's no carbocation, it's probably anti-Markovnikov, which we're going to look at. Email me and I'll send you the specific links. So let's look at the reaction I showed you before, but this time actually looking at the mechanism. If I have a molecule that has an asymmetrical alkene, asymmetrical because this carbon here is tertiary and this carbon here is secondary. If I have, let's start with just one of the simple ones, an HBr reacting. HBr is a strong acid. We have a bond between hydrogen and bromine that is not very stable the moment it hits solution because the bromine is trying to pull the electrons away from hydrogen. This is very partially negative, very partially positive. So partially positive that this pi bond puppy on a long leash gets excited, reaches out, and attacks. When the hydrogen gets attacked, the bond between hydrogen and bromine breaks because hydrogen can only have one bond. And now we have a choice of 2 different intermediates. When the pi bond breaks, one of the carbons winds up holding that hydrogen. And so I can put the hydrogen here, or I can put the hydrogen here. The other carbon is left empty. It lost the pi bond. It got nothing in return. And so the empty p orbital is deficient. That gives me my carbocation. So these are the 2 options. Br minus is off somewhere in solution, happy and unbothered, so we're not even going to worry about it. This is what we're looking at. This right here, carbocation formation in any reaction, alkenes, not really alkynes, although some professors will show it with a carbocation, substitution, elimination, all of that. This is your rate determining step. This is the slow, takes forever for the carbocation to form. And then once the carbocation formed, the next step is really, really quick. So this is all we care about for figuring out the product. Which one am I going to form? Well, what do I have? For the first one, I have a secondary carbocation. For the second one, I have a tertiary carbocation. We know that tertiary is more stable. And that means this is the carbocation that is going to form. The other one is not going to form, or it's going to form so slowly by comparison that maybe one out of a very, very big number goes secondary, this is the product that you're going to get. That Br minus that was off somewhere in solution happens to bump into that carbocation at some point almost instantaneously. Why is that not erasing? Almost instantaneously, can't speak today. After it forms, it attacks right over there. Too much green today. I seem to be in a very green mood. It attacks almost immediately, giving me a product that looks like this, with bromine having added to the more substituted position. Hydrogen over here we don't show because hydrogen inline structure is invisible. And this is the product as opposed to the one that we would have gotten the other way with a bromine here. So this right here is called the Markovnikov product, or we'll call it Mark's product, because it follows Markovnikov's rule. And if we go back to the previous definition, hydrogen went to the less substituted, nucleophile to the more substituted, hydrogen rich gets hydrogen richer. That one is because we have one hydrogen here, and now it got richer with the second one. But those are all just memorization tips. What I want you to recognize, and let me know, fire emoji in the comments if you're with me, it's because the carbocation formed at the more substituted carbon that the incoming nucleophile happens to have wound up at the same place. As for endo or exothermic, I don't know. I've never looked that up. So if your professor wants you to know something like that, make sure you do look it up. Question about anti-bonding. So we're not going to go into bonding and anti-bonding orbitals here. We're going to focus just on the strict understanding of the mechanism and the what and why behind it. So it looks like we are on the same page. It looks like we're clear with Markovnikov's rule. The takeaway that I want you to get from here, the more stable carbocation is going to form. And by the way, the nucleophile will attack there. Why is the hydrogen on carbon 4 listed at sometimes and not listed on others? So if you're talking about the hydrogen that I'm showing, I don't know what, carbon 3 is where I was drawing hydrogens. I'm showing you the options of where it can go. And here I was showing you both of them for the rich get richer mnemonic, but you don't need to show hydrogens for line structure. Question. Is the only product being formed is the tertiary carbon, or would there be a major or minor products? No, in this case, you're not showing major or minor. You're only showing one product. And so that's a good point. I meant to cross this out. That is not going to form. This one is going to form. All right. So now that we have the basics, let's go through the alkene reactions. We're not going to go step by step into all the mechanisms. I'll just show you the key components. And then, of course, the shortcuts, because if you're not asked for the mechanism, you do need to know how to come up with a reaction quickly. As I told you in email, don't waste time on the mechanism if you're not asked for it. So we'll start with hydrogenation. I said it as hydrogenation because hydrogen is H2, and that's the first reaction. The easiest way to show all the good things will be with an asymmetrical ring, because that will allow us to very easily see, let's do it like this, that'll allow us to very easily see regioselectivity and stereochemistry, meaning syn or anti-addition and Markovnikov or anti-Markovnikov product. Whoops, did not mean to do that. What did I mean to do? I meant to do, why do I keep doing that? Where's my copy? There we go. So we'll put a pi bond here. And for this reaction, we're using metal as a catalyst to add H2. For example, palladium, platinum carbide. Those are, I think, the most common ones that you've seen. And the question is, where do the hydrogens wind up on the product? Actually, it should do. Okay, that should do it. We just finished talking about Markovnikov's rule, except in this case, we have two hydrogen atoms that are adding together with no carbocation intermediate. And typically, if you don't have a carbocation intermediate, you're very likely not going to have, let's try gray for silver metal. You're not going to have Markovnikov's rule. So this right here is a metal, and the metal on its surface just grabs a bunch of hydrogen atoms. They are attached. Now, what I want you to picture is that when a pi bond gets close to that metal, why am I drawing so small? I keep reminding myself, students are on a cell phone. You gotta let me know if you're on a computer, tablet, or a cell phone watching this. So I'm going to try to remember to draw bigger. We have the pi bond that happens to get very, very close to that metal catalyst. And what happens is the metal will grab the carbons like this. Two hands just reach out and grab it. Question for how often I go live. I try to go live weekly unless I have things going on. Like last week, I was beat after my marathon, so I didn't go live. And then holidays and whatnot. Okay, I'm seeing a lot of computers, laptop, and a couple of phones. Okay. And so in this case, the metal grabbed the alkene together. And then what happens is the hydrogens will kind of just slide over. And so because the metal was grabbed from the same face, so let's pretend that this is a ring or something similar, the hydrogens will slide over together on the same side. And that means we're going to get a syn addition. So we'll add the hydrogens either coming both forward, or we'll get the hydrogens both adding back. And let's not forget our methyl group. So when hydrogens add forward, the methyl gets pushed back. And then we'll put another one because we're going to have two potential products unless your product is achiral. And well, in this case, actually, the product is achiral. So let's make it more exciting so that we do have a, do you see how this is achiral? Because these are just hydrogens. So my product is just turning a cycloalkene into a cycloalkane. But if we add a methyl group here, now we've given this molecule stereochemistry. Now I have to show both of them because the two methyl groups can be on the same face or the opposite face. This one never changes, but if the hydrogens add to the back, then this one right here, let's put the CH3, this one right here comes forward. We have a hydrogen here and a hydrogen here. The fact that they add to the same face, both are on wedges or both of them are on dashes. These are called, this is a syn addition product. What is the relationship between these two molecules? Timonium, I like your handle. No worries about being late, better late than ever, right? Ask me about the marathon after because I don't want to derail this whole session, but I can talk about it forever. It was so awesome. It was absolutely awesome. In this case, the two molecules are enantiomers. No, they're not enantiomers. No. Enantiomers is when you have exact mirror images. But in this case, when you have at least more than one chiral center, where one is the same and one is different, we have the same. And here we have the opposite. They are not both the same or both different. This makes them diastereomers. I have seen professors make mistakes like this, and they'll call them enantiomers. They are diastereomers because we have one the same and one different. So what question I have for you here is, do you see why the hydrogens add syn, even though there's no Markovnikov situation to consider here? And I want to show you one more trick that professors like to do, and I'll show it to you with a shortcut. So we'll take that same starting molecule, but this time we're going to react it with D2 in a palladium carbide catalyst. So to come up with a product here, the question, first of all, is what the heck is the reaction? What is D2? Deuterium is an isotope of hydrogen. It's just heavy hydrogen. Hydrogen has one proton, no neutrons, so the mass is 1. But if I have one proton and one neutron, the mass is 2 or D or dos or something that starts with a D. That's where I get deuterium. It's just heavy hydrogen. Professors like to use deuterium on exams because they want to see that you know where the hydrogens go. In the last one here, what I didn't show you, but you should understand, is that there's a hydrogen here There's a hydrogen here. And so if I didn't have this methyl originally, then the product was just a reduction. We just have a methyl group, nothing else. But by adding the deuterium, now you have to show deuterium versus hydrogen and where they go, which makes the problem a lot more complicated. So we'll show deuterium on wedges. That means we can have hydrogen on a dash. We can have the methyl on a dash like this. And then you also have the opposite of this one. In this case, we have stereoisomers again. What is the relationship between them without that extra methyl group that I gave you before? Deuterium on a dash, deuterium on a dash, and this hydrogen does not have to be shown. I was just demonstrating. Questions in the meantime? Yes, the live streams are posted to YouTube, so you'll have access to them right away. Will we get a cis product with palladium carbide? So I want you to be careful. Cis is when we refer to two substituents on the same side. Syn is when we refer to two groups adding on the same side. Hydrogen, deuterium, these are not substituents. And so this is called a syn rather than cis addition. But a lot of times cis actually does look syn. Syn does look cis. All right, so these are enantiomers because now we have the exact opposite. Every single chiral center is exactly reversed. And so we have the opposites. I kind of jumped into it without showing you the shortcut, but the shortcut for a hydrogen addition is very easy. All you do is break your pi bond and then draw two wedges or draw two dashes if you're showing both of them, and that's it. The other piece to this reaction is whatever was on there, put it opposite the hydrogens that you added. So if I do a syn with wedges, put the methyl on dash, syn with dashes, put the methyl on wedge, and we are good to go. This was a pretty simple, pretty straightforward one. So hopefully we are on the same page. Let's jump on over to hydrohalogenation, which I already showed you before. So we'll go back to it. Hydrohalogenation. These words are so long. Okay, so for hydrohalogenation, we have hydro again, which is hydrogen, and halogen, which is X. The halogens that you're going to see here are chlorine, bromine, and maybe iodine. But for the most part, it's chlorine and bromine because fluorine and iodine just don't play nicely with these kinds of reactions. What we have is, I already showed you the mechanism earlier, so I'm going to show you the shortcut here. I'll make the alkene asymmetrical. I was going to do rings, wasn't I? We'll start with this, and then we can make it asymmetrical on a ring after. Let's react now with HCl, because we already saw HBr. We know that the reaction has a mechanism where the hydrogen gets grabbed and the chlorine breaks away, and we have the carbocation, all that good stuff that wastes a lot of time. We cannot afford that time on exams. And so what we're going to do instead here is the shortcut. Oh, I meant to say put shortcut in the comments if you want to see the shortcut, but I got ahead of myself. So we draw the skeleton without the pi bond, break the pi bond, quickly identify if you have an asymmetrical alkene, which is more substituted and which is less. For this one right here, we have a tertiary carbon. Here we have a secondary carbon. Without drawing the mechanism, without drawing the carbocation, just remind yourself, this molecule will undergo a carbocation intermediate at the tertiary more substituted position. That means the nucleophile is going to follow the carbocation. That means the nucleophile adds right here, and that is my product without the mechanism. I immediately got to the right answer because I understand that Markovnikov's rule is about the stability of the intermediate. Question on the previous reaction. Hydrogenation is always going to be a syn addition. Yes, because the metal holds it from the same place. The hydrogens slide in, and they never go opposite because the metal is holding on just from the same face of that carbon bond. Enantiomers because there is a mirror image. Yep, that is correct. So we have our hydrohalogenation. And in this case, the molecule that I gave you is achiral. The product is achiral because this one right here has two methyl groups, so it doesn't matter. But what if we look at it with a ring? And so we'll have this right here. Professors love rings. They love to scare you. I'm showing you the rings to show you the logic holds even without a ring. So don't worry about a ring. And let's react it with HBr. We'll do the same thing here. The shortcut for this, draw your carbon skeleton, but the main skeleton, anything on the pi bond, hold off on that. So just draw your carbon skeleton without the pi bond. Identify your substitution. So in this case, we have a tertiary carbon. In this case, we have a secondary carbon. Recognize that the carbocation will form here at the tertiary position. That means the bromine will come here at the tertiary position. So we'll add the bromine. We're going to need a methyl group. Otherwise, this is going to be achiral. If all I did was add a bromine, it would be achiral because there's nothing else of symmetry on the molecule. So that's why I added the methyl group. Let's put it back here. And now, what do we do with the bromine? Bromine can add to the top or the bottom. Unlike the hydrogen from the previous reaction where they were forced there by the metal, when we have a carbocation intermediate, let's go back to where I showed you the carbocation. If we have a carbocation intermediate, what is the hybridization of that intermediate? What does that look like? A carbocation, that carbon is sp2 hybridized. sp2 carbons are trigonal planar. That's the fancy term the professor wants you to know. We're just going to call it flat. And if it's flat, the nucleophile could come in from the top or the bottom. It doesn't matter, equal probability. And so I can put the, why did I put a bromine there? I can put the incoming bromine at the top or the bottom. And in fact, I'm going to have to show both of them. Let me not, what did I do? Let me not keep worrying about that and just make it substituted. There we go. So I have to draw both of the products with one bromine at the top, one bromine at the bottom, meaning one on a wedge, one on a dash. I don't have to show the hydrogen, but now I do need to go back to any substituents that I had. If bromine added from the top, methyl got pushed down. If bromine added from the bottom, methyl got pushed up. And these are my two products. Once again, stereochemistry here, because the molecule is no longer symmetrical, having added that methyl group there. The methyl group on the bottom has not changed, but the stereochemistry at the top is opposite. One chiral group is the same, one chiral group is opposite. That makes these two molecules enantiomers to each other. And then the hydrogens, well, we don't care about. Is this a syn or anti-addition? The answer is neither, because that hydrogen added first, and we don't care which way it added compared to the hydrogen that was already there, because it just adds to either face, and then we have a flat carbocation. So the bromine adds top and bottom. We're going to get both. Let me go back to, let me show you one more so I can, trying to show you all the different takeaways. And so we need a bunch of different molecules for them. For this one, we're going to do, I don't want two methyl groups. I don't want it to be, okay, there we go. We'll do that. Nope, that's just two methyl groups on the other side. I am looking for, I want just one chiral center, right? So if I want one chiral center, then I'll put a ring on it. There we go. A ring is one way to guarantee it does what I want it to do. Or I could have just done that. Okay. All right. This is what happens when I am making up problems. I'm like, I want this on it. I want that on it. There we go. We just simplified everything. We'll keep the ring for another problem. By the way, I'm trying to keep it here as simple as possible so I can teach you the concepts. But you want to make sure that you do more complicated practice, lots and lots of practice, so that you get really good at it. I have an alkene practice set. Just put alkene practice in the comments and I will give you a link. This way you can try everything we did on more tricky problems afterwards. All right, so we'll take this molecule right here and we'll react it with HCl. I have not been giving you reagents, so we'll put CCl4. CCl4, the key here is it's an inert solvent. It does not react, which is really, really important, because if it does react, we get a different product. In this case, we'll do the shortcut where we start by drawing the carbon skeleton exactly as we see it, minus the pi bond. Identify the carbons holding the pi bond. We have secondary, can form a carbocation. Primary will not form a carbocation. And so we put the chlorine at the secondary position. I will randomly put it on a wedge. Recognizing that this is chiral, I also have to put it on dashes. Some professors will accept the answer where you just draw 1 and then write plus an enantiomer, or you draw it with a squiggly line like this to show that it could be dash or wedge, and again, put plus an enantiomer. How many wedge and how many dash am I going to get in a situation like this? Question, how do you know when the molecule on the bottom is inert or not? That is a very, very, very good question. I'm not going to go into too much detail right now, but typically what you're looking at is polarity of the molecule and the ability of hydrogen bonding. In the substitution elimination series, I have a video on polar protic and aprotic solvents where I go into detail. So make sure to watch that one. Actually, let me put it into the description here. All right. If you're watching the recording, the link to that video will already be in the description. And so if there is polarity, the polarity has it interacting, which I'll show you in a future reaction. But if it's something like this, CCl4, the bond is not polar, it's got the whatever polarity between C and Cl is completely canceled out. This is not going to want to attack the molecule or the carbocation. Back to the products that we have. We are going to get an equal mix for the most part, 50-50, 50% R and 50% S. So it's almost like they're racing. How many R's can I get? How many S's can I get? They're racing, and that is how we get a racemic mixture. So this product is chiral racemic, meaning it's chiral, it's got stereochemistry, but it's racemic because we have an equal mix of R and S. 2 possible isomers due only to 1 chiral center. That is absolutely correct. Right, so we focused on this one reaction, but what I want you to take away from here is just all the different outcomes that you can have. Whether it's chiral, it's achiral, the shortcut, when you get enantiomers, when you get why did I call that enantiomers? These are not enantiomers. These down here are enantiomers, but up here is not because these are opposite. These are the same. When one is opposite and one is the same, they are I do not have room for that. Diastereomers. There we go. Question. Why does the butane and chlorine on a wedge have a carbocation, but the one on the right with a chlorine and dashes does not have a carbocation? Oh, these are not carbocations. Thank you for pointing that out. Let me make sure my asterisk is drawn like an asterisk. I had a student who used to call them the asteristicated carbon. Asteristicated because it's the chiral carbon. The asterisk is showing that the carbon is chiral, but by the time you get to the product, they have no carbocations, no charges, because they have to be neutral. Would it be racemic if there were 2 stereoisomers? These are 2 stereoisomers. One is R, one is S. Or did you mean in this case, these are also racemic because we have these 2, equal mix between R and S for the top? So let me know if that clarifies if that makes sense. And then let's see if we can apply this logic to, well, no, not really, because the next one is a completely different reaction, the dark reaction. Also, hydrogenation. All right, so I'm sorry, this is we already did the dark reaction. Let's go back here. So this reaction here does not have any special conditions as long as the solvent is inert. And typically what you're going to see here is CCl4, CH2Cl2, some combination of carbon and halogen and hydrogen on a molecule, or no solvent at all given. This right here is called the dark reaction because we're not going out of the way to add light to it. No one teaches the dark reaction. I teach the dark reaction because what you're going to see is the light reaction. And if you have a light reaction, you want to know the difference between that and the dark reaction. So if I take that same starting molecule with an alkene and, well, let's do the first one that we did because radicals like to have more substitution. And I react it once again with HBr. But this time I add heat, I add light, I add peroxide, I add conditions that are very, very extreme. You are going to get a very specific reaction that is exactly opposite of what we had before. Bromine is going to add here. This is an anti-Markovnikov product, not to be confused with an anti-addition where they add opposite, because in this case, there is no syn or anti anytime you have an sp2 intermediate. Anti-Markovnikov just means that the bromine added to the less substituted carbon. So my question to you is, why did bromine go there specifically in what we're calling the light reaction? Alexis, long questionable. I don't see your question, so if you can please type it again. The chat scrolls on my screen, and so if I don't see it within a couple of comments, then I lose it. But if you type it again, I will try to answer them all. Okay, so in this case, interestingly enough, the same reasoning that gives us Markovnikov's rule gives us this anti-Markovnikov product. If you go through the mechanism for this, this is a radical reaction, and I do have a video showing you the step-by-step, so I'm not going to go through the mechanism here. But what happens in the first step is we form a radical, and bromine adds first. The halogen adds first, and the hydrogen adds second. And that radical, you'll notice, is most stable when it's going to be most substituted. Just like carbocation stability, radical stability requires a more substituted carbon intermediate or more substituted radical intermediate. And then hydrogen happens to add next. So H adds to the radical. And if the radical happens to be on the more substituted carbon, it adds to the most substituted carbon. So it follows the same principle of most stable intermediate, and that last piece adds wherever there's an opening, which happens to be at the radical position. So the shortcut here is you break the pi bond, you put your nucleophile first, this adds first, less substituted carbon, and then the H is second on the more substituted carbon because that's where the radical goes. Question. Is it safe to think of where the hydrogen go like this? Which carbons need something once the pi bond is broken? So once the pi bond is broken, hydrogen adds first, and then the nucleophile adds second. So the carbon that needs something, which if you're thinking about it as the carbon that needs something for the last step, the nucleophile, then yeah, that is one way to think about it. Just make sure you're clear on which step you're at. Which step you're thinking about. So anytime you give yourself a mnemonic, just make sure it's not something flat, like you just have flat memorization. Make sure it makes sense. It connects to something. It connects to something logical there. Anthony, thank you so much. I appreciate that. All right, so we have the radicals. This is the exact opposite of the regular halogenation reaction. And let me make sure to put the radical here because this is also called just radical halogenation. It's not really called hydrohalogenation, but it's basically the light reaction version of the hydrohalogenation. All right, let me know if you're with me so far, because for the next reaction, you know what? I don't have this one on my notes, but for the student who asked about the inert solvent, I'm going to show you this one. This is a fun one that professors like to use to trick you, and for some reason it's not taught because it's like a cop-out reaction. If I react HBr in, say, water, the product is going to be very unexpected. This is Alexis, right? I just want to make sure I'm referring to the right student. And yes, if that's you, Alexis, yes, that makes sense. This right here is very interesting because the inert solvent is going to get in the way. It's a busybody, and that's a problem. So the mechanism starts out as usual. The hydrogen gets grabbed. We form a carbocation intermediate. Hydrogen added to the less substituted carbon, carbocation formed here. And Br minus is off somewhere in solution, happy that it got the negative charge it wanted. But Angel, okay, sorry, I was confusing you with someone else. And thanks for clarifying. So we have Br minus in solution. And in an inert solvent, Br minus would be the thing that attacks. But what happens when I have water is going to completely surround and cage the bromine. And this bromine is happy, distracted. It is not going anywhere. It is partying. And so this carbocation is left on its own, waiting for something. And the something, Angel, absolutely correct, is a water molecule. Because when you have nothing negative available, the most negative thing is the oxygen and the lone pair electrons on the oxygen that will come in and attack. And when that happens, let's kind of wind our way around here. When that happens, you're going to get the oxygen with its two hydrogens over here, one lone pair and a positive charge. Another water molecule will come in and deprotonate, giving it back its electrons. And your product is a completely unexpected alcohol. Nothing to do with the halogen that was there. This is simply acting as an acid catalyst. An acid catalyst and alcohol is the product. I will see this show up on my students' quizzes and exams as a trick question rather than a question that you have to learn. Like this is another reaction. But this is why we have to pay attention to a solvent that is not inert, because it gets in the way, as we saw here, and gives you a completely unexpected product. Nothing to do with it at all. It's really silly, but it shows up all the time. Exactly. So I want you to be prepared for it. The next reaction I want to look at is halogenation. And I used to confuse this until I realized we need a hydro in front of anything if I want the hydrogen. Halogenation is just halogen. That is my X2, which will be Cl2 and Br2. No I2 or F2. Those are not, they don't have the right reactivity. They're either too reactive or too unreactive. Nicole, you did pinnacle rearrangement at this level? Wow. That's a fun one, especially the mechanism. All right, so let's look at hydrohalogenation. And for this one, we don't even need that methyl group because we can just look at what is happening. The regio selectivity here, not even the regio, the stereochemistry is interesting. So we'll take something like Cl2, and I'll show you some quick pieces of the mechanism because it's a very dramatic reaction. If you can picture, instead of atoms and molecules, picture people. So we'll use, my son is almost 4, and any examples I've done in the past, forget that. We're just going to talk about toddlers and little kids, right? These kids, so we had a play date over the weekend. The number of times these two boys butted heads and made each other cry, and then they come home and like, I had so much fun. If someone had made me cry when I went to hang out with them, I'm never going back. But apparently toddlers are like molecules. So here's what happens. The pi bond is very curious. It's got the negative electrons. It sees something positive or partially positive. But wait a minute. Positive or partially positive? We're looking at a molecule, halogens. 2 halogens are very, very electronegative. So what about it is positive? Well, as the pi bond gets close, for that fraction of a second in time, the electrons from chlorine get scared and they just run away to the other side. My son, all day, he wants to play with this kid. He wants to play with you, wants to play with him. We get to the kid's house and they're both hiding. One hides on the couch, one hides behind me. It's like, you guys wanted to play together. Why are you hiding? So they run away and they hide. For that fraction of a second in time, that chlorine is ever so partially positive. And that is all the pi bond needs to take advantage and attack the chlorine. When it does so, that chlorine is like, you did not just do that. And it immediately attacks right back. You attack me, I attack you. This one's like, I'm out of here. I want nothing to do with this at all whatsoever. For the intermediate, and of course I have a methyl group and I don't want it there. For the intermediate here, what happens is the chlorine forms two bonds, either at the top or the bottom, wherever that initial attack happened, because chlorine attacked. Whoops, that was very dramatic. Chlorine attacked and got attacked. So it forms a bridge. It is very unhappy. It has a lot of regrets for what just happened because chlorine, an electronegative atom, stuck a positive charge. Not happening. That other chlorine, though, got over the shock of everything going on here. It's like, I want to play too. I want to have a turn. This chlorine is so unhappy. It pulls and pulls and pulls on the electron density between itself and carbon, making both carbons very partially positive. Now, I showed you an asymmetrical carbon. I showed you a symmetrical molecule. But if it was asymmetrical, the more substituted would be more partially positive because it can handle that charge better. So that is where the attack would happen. And if chlorine wants to come in and attack from the top, it can't, because if the other chlorine is there, it's in the way. So what it has to do is kind of go all the way around, find its way in, do a sneak attack from the back, and break that bond. So for something like this, let's draw it here. What we get is one chlorine having added to the top. That bond was not touched. It's still there. The other chlorine attacked from the bottom, or if it was bottom first and attacks from the top. The idea is they have to be opposite from each other. And this right here is why, not because you memorized, but because you understand that bridged intermediate is why we get an anti-addition. And the molecule is chiral. We have stereochemistry here. So I would have to show a second one where I have the first one on dashes and the second one on a wedge. Light bulbs in the comments if you get why behind the anti-addition for the halogenation reaction. Chloe, you are very welcome. You can catch the rest whenever you have time to catch up. I realize that we are going to go past the hour today, but this is a fun topic. I'm feeling very fired up today. So if you guys want to keep going, we'll keep going. And yes, we have, so first of all, these molecules are enantiomers because I have nothing else here to make it a diastereomer. And they are racemic in that we have, well, racemic typically refers to 50-50 RNS. So I don't know if you would call this racemic, but technically, yeah, you have 50% of one and 50% of the other. Anthony, hopefully not after today, not after, well, for this topic. And of course, all the other topics, we can tackle those one at a time. Is this what happens in an electrophilic addition reaction? This is electrophilic addition. Yes. Electrophilic electrophiles are getting added. Keep going. All right, let's do it. I have not seen anyone say stop, so let's continue. If you're joining late, don't worry about copying all the notes that you see. Just put live notes in the comments and I'll give you a link to get a PDF of everything you see me drawing today. And put Alkene practice if you want to apply what you're learning today to lots and lots more practice problems, including some tricky ones. We're not going to get to ozonolysis today because then we'll never finish. And I do want to go to sleep soon. I have been just so exhausted. The marathon was over a week ago, but I am still pretty drained. And tomorrow's going to be a long, fun day because my kiddo is off for Veterans Day. So I need to rest up. All right, so let's see what happens. Now, oh, shortcut. Let's do shortcut. Ooh. Put shortcut fire emoji in the comments if you want a bunch of shortcuts that I didn't have on my notes, but I just thought of as I was saying shortcut. I am really excited about this topic today. So let's say we have a molecule that looks like this. And we're reacting it with Br2. All right, I see shortcut fire. Let's do it. First, the simple shortcut. We break the pi bond, redraw the carbon skeleton without it, and then draw your molecule anti. One up, one down, meaning one wedge, one dash. But then you'll see a problem on your exam where the professor says, show me the starting molecule that will give me a product that looks like this. And you're shown a chlorine and a chlorine. Well, I just finished telling you that this is an anti-addition. So how the heck do I get this? This is them testing to see if you're paying attention. This molecule right here is capable of rotation because sp3 and sp3, the carbons can rotate. And so if I rotate this molecule, let's make half of it blue. So we'll rotate the blue half. We'll keep the purple half as we see it with a chlorine up here. And this is the piece that rotated. Up and out of the page, 180 degrees is going to give me down and into the page. Down plane of the page, 180 degrees gives me up plane of the page. And wait a minute, doesn't this look like a nice anti-product? Now you know how to do this. You say, oh yeah, this one just started with a regular old trans alkene reacting with Cl2 in something like CCl4. But what if the molecule is more complicated? What if you didn't want to take the time to do the rotation? First, let's go with the well, what just happened? The trick won't make sense if we don't break it down first. So let's go back to this one. So we have this starting molecule, and we know that the product will look like this. So let me move this down and show you the bromines because that one is drawn very neatly over here. We know that this is the product, right? Let's first make sure we're on the same page with the product. If I take this molecule and recognize that I have sp3, sp3, this bond here can rotate. And things that are up go down, things that are down go up. So in my model kit here. So take a look at this model kit. Here we go. All right, so I have, just forget all these substituents on it. It's going to be stereo session. My son finally stopped taking my model kit, so I have some. So we have our product like this. We have one up, one down. These are my two bromines. But this right here, this bond can rotate and rotate and rotate. And so now it appears to be a syn addition. Now it's an anti. Now it's syn. Now it's anti. It's just a matter of rotation. So if I rotate it on paper, we'll take this half and keep it exactly as it is. So that will be this right here, bromine on a wedge. This is the bond that rotated. This half, we're going to do a 180-degree rotation. So we'll do 180 degrees. And that means bromine down in the plane of the page, down into the page is going to be up and out of the page. Methyl up in the plane of the page is going to go down in the plane of the page. This is the logic. If you understand the logic and you now just want to quickly and easily come up with a product, all you have to do is remember that a Trans Am is a cool car. I did not know about a Trans Am. I was teaching the car mnemonic, and then my student told me a Trans Am was a car. Looked it up. Now that's a much better mnemonic. Why do we care about Trans Am being a car? Very simple. If I have a pi bond, that is trans, and I do an anti-addition, the product is going to be meso. But if I have a cis molecule undergoing an anti-addition, the product is going to be racemic. So let's take a look at what we have here. Let's just use this one. I have a trans alkene undergoing an anti-addition, and the product, trans anti, when I rotate it, is this not a perfect meso compound? And yes, it can have other substituents, but the way that the chlorines add, you get that meso. If, however, I started with a cis anti-addition. Let's do this right here. And I react it with Br2 and CCl4. Now my product is going to be racemic, because if I put, let's keep the colors consistent. Oh, lost my whole thing. So I need to draw two of them for the racemic product. I'll have bromine on a wedge and another one on the dash. Bromine on dash, another one. That's not, what am I doing? There we go. And another one like this. There is no symmetry. There is no meso. If I rotate it, this is where the trick helps, because when you rotate this thing, it's not immediately obvious, because now they both seem to come out of the page. Not they both seem to. They are both coming out of the page. Or in this case, it's reaching for green. In this case, we have one going into the page, this one going into the page, but there's no symmetry because these appear to be the same, but these are opposite. So that's where, if you just use this mnemonic, you can come up with the products and the correct stereochemistry without having to draw the rotations. All right, Jeff, this one's for you. Angel, thank you so much. Yeah, I'll talk about that at the end for anyone who's interested. I swear my professor is trying to kill me. Well, we are going to save that. We're going to change that. We're not going to let your professor kill you. And Noel, thank you so much. And Angel, thank you so much. I appreciate the kind words, and I love having you two in the group. I'm actually, just a heads up, I'm actually planning to choose a topic for the November worksheet. So you guys have to make sure to vote because it's coming up soon. Okay, so we have this reaction. Now let's go back to those pesky solvents that are not inert and tend to get in the way. So here we have our alkene minding its own business, trying to react with the Cl2, as we've seen before, except you're going to get a very, very, very unexpected product. What happens here, we'll jump straight to the intermediate. I have this right here. Chlorine got greedy. We formed a chloronium bridge. And water happens to be the solvent. In the previous reaction, we had a Cl- that came in, did a backside attack. So let's show this on wedges. That means this thing would have gone dashed. We had a backside attack, and then we got both halogens adding, except we already saw what happens if you put this into a polar protic solvent like water. And yeah, that chlorine is not going anywhere. Instead, it's another water molecule that is going to attack. And the water molecule is looking for that partially positive carbon. Because this is an asymmetrical starting molecule, the more substituted, the more partially positive, which means water is going to be very specific in the region that it attacks. That's where regioselectivity comes from. Breaking this pi bond, giving me a product that has, we'll start with the alcohol. We'll put the OH on a wedge. That means the methyl here went dashed. And then the chlorine is going to be opposite because this is still a backside attack. So what we have here is a couple of key things. Technically, this is considered a Markovnikov product. It follows Markovnikov's rule because even though it's not a carbocation, it's a partially positive carbon where the oxygen adds, and the incoming solvent molecule attacks at the more substituted, more partially positive carbon. And we also have an anti-addition. Now, I want to be very careful. This is not anti-Markovnikov. Markovnikov's rule, anti-addition in how the two relate to each other. One went on a wedge, one went on a dash. Plus, we're going to have the enantiomer, which I kind of drew myself out of room here. So we'll do it like this. But we're never going to have the OH on the less substituted carbon because it still has to follow Markovnikov's rule. This right here has a halogen, making it a halo. And the water portion is called a hydrin. This is a halohydrin reaction, a halohydrin formation. Why is the Cl dashed? The Cl, very good question, is going to be opposite. Now, I showed you the mechanism here. I showed this to you up. This is not the intermediate for this one. This would be the intermediate for here. I kind of showed it just an intermediate, and then I showed you the two products. But what happens is the bridge forms, the more substituted carbon to halogen bond breaks, and then you get your product. There you go, Anthony, and good luck tomorrow. Okay, so for a couple of students who asked, this is just an intermediate for the reaction, but you have two different products forming. Any tips for studying mechanisms? Let me put a link for you in the description. Okay, do that and you'll find it much easier. Okay, is the trans-M shortcut only for hydrohalogenation reaction? It doesn't work with additional reactions as well. It works only for reactions that will have syn or anti-addition. So let me show you how we can, for example, use this for a halogenation, a hydrogenation. If I have something like this, I can say if cis anti gives me racemic, then what is the opposite of that? Cis syn would give me meso. Trans syn would give me racemic. So you can flip it like that, and therefore you can say that if I react this with H2, then we know this one, which is why it's an easy one, but I'm showing you how you can flip it. Notice that the two hydrogens adding gives me a meso compound, cis, syn, meso. So as long as you don't have a carbocation intermediate, this works. Quick, cis, trans, easy, anti, or syn. Okay, so this is a really good question that I think is worth a detour. Oh my goodness, we're going to be here forever tonight. All right, but I like your question. So E and Z is when you have substituents on your pi bond. Cis and trans is when you have one carbon chain or subs on a ring. I know this is very confusing because it should be just this or just that, but no, it's a little bit of everything. So when we're looking at E and Z, we're looking at something complicated, like a pi bond with, say, a chlorine here and other things, right? So now you have to rank them all this way. Cis and trans would be right there is trans, right here is cis. I could have anything on the ring. Right there is trans. And right here is cis. But the reason I wanted to bring this up is what does this have to do with syn or anti? Syn or anti specifically has to do with how we're adding across a pi bond. And so it's not about what I see. With EZ, cis, or trans, I can freeze that molecule in time. No reactions to look at. I look at the molecule. Is it E or Z? Is it cis or trans? With syn versus anti, this has to do with incoming groups. So it's not about the final product. It's about what came onto the molecule. If I have my ring and I brought in, so we'll do a Halohydrin for this one. We'll do Br2 and H2O. Oh my goodness, I'm like finding myself trying to give you so many more examples, but I'm gonna be disciplined here and say we're not gonna go all night. We're just gonna go a little longer. But I was gonna show you. Oh man, put backpack in the comments if you want the backpack trick, because I'm not gonna have time to teach that. So for this one right here, if bromine adds here and the OH adds here, it's not the fact that they happen to be trans to each other. It's that the fact that they added anti to each other, the mechanism of attack put them opposite, and that is why it's called an anti-addition. Now here it looks very obvious. You can say, hey, this is a this is a trans molecule that is an anti-product. But what if I gave you something that looked like this? And this is why I think it's a very good question, because professors will do that, where you have, say, a methyl group here and an ethyl group there. And now you're reacting it with Cl2 in CH3OH, backpack trick for the win here. I'm going to fly through it, but you'll have to check the link for the specifics. In a situation like this, you break the pi bond. You draw your incoming group. So we'll choose randomly to put the chlorine on a wedge. Therefore, the incoming nucleophile, backpack trick in summary, drop the hydrogen that gets deprotonated, add the nucleophile, in this case, the oxygen, and the backpack is everything attached to it. But we still have a methyl and an ethyl. So this right here, the methyl goes this way. The ethyl goes that way. And there are plus more products. I could have done the opposite here, or the chlorine could have added here. So there are a total of 4 products here, which we don't have time to do today. But I challenge you to try them on your own. So right now, we can't say anti or syn is trans or cis because we have a mess going on here. So what we're looking at here is the fact that the incoming groups added opposite to each other. That makes this an anti-addition regardless of the stereochemistry of the final product, meaning we don't care what is cis or trans or E or Z to each other. We just care about how the 2 groups that came in added. Let's see if that was a very good question. Let me know if that makes sense. And for anyone else who was wondering, let me know if that helped, because I think that's a really, really good question to have dug into. Amaya, yeah, I try to put a poll up a day or so before, so students help me choose the topics. We're going to have to save ring expansions. Maybe we'll do something like that next week, because we can keep going forever. And I don't want that. So we did Halohydrin. You know what we'll do? We'll finish with this really interesting one. If I take my starting molecule and I react it with this or this or this, I can get an alcohol for my product as follows. 1, 2, and 3. Alcohol number 1. Nope, that's not the starting molecule that I want. And this is very, very important to pay attention to. Oh, I'm getting so many good ideas. I need to do a worksheet, because then, oh, good, I do not have time for a worksheet. Stop saying that. Ignore what I just said. I don't have time for a worksheet tonight, but I had some good ideas for problems. Okay, so we have an alcohol that we can put over here, and over here. So here's what happened. The pi bond sits between these 2 carbons. This one is primary. This one is secondary. This one is tertiary, but no pi bond right there at all whatsoever. And this is why it helps to understand the mechanism. So let's take a quick look at what the options are, and then we'll look at the shortcuts for each of them. For the first one, notice that we have an anti-Markovnikov product, because the incoming nucleophile, the alcohol, added to the least substituted carbon. This right here is hydroboration. That is BH3, THF, step 1, step 2, NaOH, and H2O2. The second one added where we have the more substituted carbon. So that means it's following Markovnikov's rule. But there's something else that didn't happen, so I'll come back to it in a moment. This one here is tricky, because yes, it did follow Markovnikov's rule, which says it goes to the more substituted, but wait a minute, the pi bond was here. This one also had a carbocation rearrangement. carbocation rearrangement implies a carbocation intermediate. And that is because this is the oxymercuration, Hg, OAC2, H2O, step 1. Step 2, NaBH4. No, what am I saying? That one had a carbocation rearrangement. That is absolutely incorrect. That one does not allow for carbocation rearrangements. What I was trying to show you here was actually just acid catalyzed hydration. H2SO4 is an acid catalyst, and H2O, or if your professor is feeling evil, HCl. Just because it's an alcohol and the HCl is just an acid catalyst. All right, so let's go through one at a time, not the mechanism, just the takeaway, so we know how to do each one. Let's start with the acid catalyst. Yeah, we'll start hardest first. No, we'll go in order. See, it's late. My brain is starting to go a bit fuzzy. All right, so for the hydroboration, we have BH3, ... We don't care about the rest. I gave it to you on top. The key here is the boron. Boron is an exception to the octet rule in that it likes to have 3 bonds, a total of 6 electrons, not 8. So the BH3 molecule is happy minding its own business. It does not mind that it has an empty p orbital, and the pi bond says, nope, I want to attack because you've got an empty p orbital. But the pi bond initiates the attack. At the same time, one of these bonds is going to break. And the key here, not that one. Let me move it a little bit so you can see. I'm not going to show you the whole mechanism. I'm just going to show you the key component of it. When the pi bond attacks the empty p orbital, this bond is going to immediately just get pulled onto the carbon, kind of like a suction, like it gets vacuumed and suctioned onto there. The reason hydrogen goes here, the more substituted, is because this thing is big and bulky. Now you're saying, wait a minute, hydrogen? That's not big and bulky, no. But boron will get attacked and attacked and attacked. All the alkenes will attack it. So there will be just trails of alkenes hanging off of boron. And when this hydrogen is replaced by an alkene, it's very bulky, so it has to hang off the side. And hydrogen is small, so it fits into the more busy portion of the molecule. Because of that, where the boron winds up, the intermediate for this looks something like this. We have the hydrogen, we have the boron, and then it's got just big things hanging off of it. The alcohol ultimately replaces the boron. And because the alcohol replaces the boron on the end of the molecule, that is how we get the anti-Markovnikov product for this. Now, well, that is probably going to be after Thanksgiving. But yes, it's on my list. Should we memorize the reactions and stuff? Yes, absolutely. Learn it, understand it, then memorize it. So we have the anti-Markovnikov, but what happens to the other hydrogen? So the hydrogen and the alcohol, even though this is considered an anti-Markovnikov, this is a syn addition. It's a syn addition because notice, just like the reaction with hydrogen, with H2, they add at the same time, so they have to add to the same face. They can't simultaneously add to the top or bottom when they're attached to each other. Instead, the alkene just kind of slides over and gets attached at the same time to both of them. So that's why hydroboration is a syn addition. H and OH add at the same face, but anti-Markovnikov. Let me show it to you with, do I still have this? Yes. So if we have something like this, we react it with BH3 and all its buddies. Here's what we get. This is the more substituted carbon. That's where the hydrogen will go. If I put the alcohol over here on a wedge, then for the product, technically the correct product, you just draw it like this, because the hydrogen also on a wedge is not shown. And this right here, you'll do plus enantiomer, And then you'll do the opposite where both of them add from the bottom. Let me know if you're with me on that one. Next, we'll look at, again, that starting molecule from before. This time we'll do oxymercuration. Hg, OAC, ... the rest we don't care about. OAC looks like a scary thing. Acetic acid is a carboxylic acid, like this. And if we deprotonate it, we get a carboxylate, like that. This group here is called an acetyl group. So this is really an acetyl, O minus, OAC. O minus acetyl group. That's all this is. Mercury bound to 2 acetates. Fun fact. When this attacks, the way that these nucleophilic attacks start out, mercury, just like bromine and chlorine, attacks back. And instead of losing a chlorine or a bromine, there's 2 acetates, one of them breaks off. So you should recognize that the intermediate here is very similar to what we saw for the chloronium and bromonium bridge. This is called a mercurium bridge, Hg. Positive charge and only 1 OAC left. It had 2 to begin with, it lost 1. The mercury is positive, but it makes the 2 carbons holding it partially positive. Which of the 2 carbons, Angel, we're going to make it easier, don't worry. Which of the 2 carbons is more partially positive given the degree of substitution? Well, the more substituted is more partially positive. The other one is less partially positive. And so the incoming nucleophile is ultimately going to attack here, Markovnikov's rule. But unlike an actual carbocation, mercury is not allowing for a carbocation rearrangement. So I think of mercury as a carbocation babysitter. Carbocation wants to move. Babysitter says, nope, I'm holding your hand. You are staying right here. And that is why it follows Markovnikov's rule without the rearrangement, as did we see before? No, as I'll show you in the next one. But because it comes in like a nucleophile, I want you to think of how similar this is to halogenation. We get the bridge, we get the backside attack, not even halogenation. This is similar to a halohydrin. This is like a halohydrin reaction. In everything, the shortcut, everything is just like halohydrin. So let's see the halohydrin shortcut applied here. Redraw the carbon skeleton as you see it. Break the pi bond. Put the incoming hydrogen, water, on the more substituted carbon. Put your hydrogen, in this case, on the less substituted, because the mercury ultimately gets kicked out. But doesn't this look kind of like we did with the halohydrin, except that would have been a chlorine less substituted and OH more substituted? And notice that it's an anti-addition. Anti-addition, but it follows Markovnikov's rule in that the OH went to the more substituted carbon. Question. So the final product for hydroboration does not have any boron. Boron gets kicked out, just like here, mercury gets kicked out. So those are just catalytic intermediates. No question is a stupid question. I'd rather you ask here than get stuck on your exam and lose points. How do we know when to include stereochemistry? Always, always, always. If it's chiral, put stereochemistry. Sometimes it's included and sometimes it's missing. So this is called, I was lazy, I forgot. But yeah, so this one right here, just to show you, this is chiral, this is achiral because of 2 methyls. What did I just do? Where was it? Okay, yeah. This one here is achiral. This one here is achiral because there are no chiral carbons. And this one here is achiral. So in this whole set, we did have 1 chiral carbon. And so we have to put that this is racemic. Yeah, just exactly. Angel, absolutely correct. that already. Guinness can help. Maybe. I don't know. All right, where were we? Last, but certainly not least. Oh, did I not put the name of this reaction? I did not. This is oxymercuration reduction, and hydroboration was oxidation. So they're redox reactions. One's oxidation, one's reduction. But I'm just gonna put this simple. And let's end on a high note for acid catalyzed hydration, complete with a carbocation rearrangement, because why not? I think I may even have ring expansion on the quiz on the practice for the alkenes. So just put alkene practice and I will send you the link. If I ever do a worksheet, I'll probably just attach it to the link as well, the same link. All right, acid catalyzed hydration. Let's use the same starting molecule, but this time we're going to have H2SO4, which is simply a source of protons in solution. HSO4 minus is unreactive. It is boring. It is a spectator. Just forget about it. It doesn't exist once we're done. And we're reacting it with H2O. We've already seen pieces of the mechanism, so I'm going to jump straight to the intermediate. Primary, secondary. Markovnikov's rule says carbocation goes to the more substituted. Terry, it is good to see you. Carbocation goes to the more substituted, and the nucleophile would add, except we want to have the carbocations be as stable as possible. So how do we do that? Here is a good trick to remember. Anytime you have a secondary carbocation near a tertiary carbon, you will get a carbocation rearrangement. Specifically, you're going to get a hydride shift. And so this molecule is not ready for the incoming nucleophile because we have a tertiary carbon right there. And unlike oxymercuration that held on to that carbocation like a carbocation babysitter, this one's a free-for-all. It can do whatever it wants. And so the hydrogen moves over. We had a hydrogen there to begin with. So I'm showing you the second one. So now we have two hydrogens. Here we have a carbocation. That is where the water molecule ultimately attacks, gets deprotonated, and we get our alcohol right there. So even though it started out between primary and secondary, there's tertiary. But how do you do this on your exam if you're not doing the mechanism? Because what did I tell you over and over? Unless you're asked for the mechanism, do not waste your time. You cannot afford the time for mechanisms. So let's take a look. If we have this starting molecule right here, and we're reacting it with H2SO4 and H2O, here's the shortcut. Break the pi bond, redraw the carbon skeleton as you see it, same as we've done before. Recognize that this is a secondary and this is a secondary. This one would be more stable to form because it's near the tertiary. And if it's going to rearrange, it'll form in a higher percentage. And so if we can form a secondary carbocation near a tertiary carbon, just look, what is near my carbocation? What is near my pi bond? That is where the carbocation will go. And that means I get an alcohol, well, that would be my methyl group, and an alcohol going to the same carbon. This molecule has symmetry, and so this is achiral. And we also don't have any syn or anti-addition because we had a carbocation intermediate. All right, so now I hope, let me know in the comments if that's the case, that you have a better appreciation for the alkene reactions that you have hopefully already studied and already understand. Your next step, of course, is practice. Now, if you need to review what we did, just put live notes in the comments. I'll send you a PDF. You'll have access to everything so you can review it. Then, if you're looking for more in-depth help for organic chemistry, not just alkene reactions, but this level help for all of organic chemistry, I would love to have you join me in the Organic Chemistry Study Hall, where you'll get access to my complete video library, Orgo 1 and Orgo 2, starting with beginner, easy concepts, meaning for every chapter, I break down the reactions mechanism step by step, build up, make it more and more complicated, lots of tricky questions, which I kind of got carried away today and showed you some, but there are so many more that you'll see in the study hall, along with all the layer for sci practice quizzes that I have on my website and the worksheets that I offer in these live streams that are free with PDF solutions. You actually get the step-by-step video solutions in the study hall. The quizzes all have solutions already. The worksheets every month, the students in the study hall choose one to work on, and we do a joint solve with me session where we go through it together. And that way you get to participate in doing the practice, getting really comfortable and being able to ask questions and see how to think about it, see how to approach it and all of that. If this is something you're interested in, the link to sign up is layerforsci.com/join. I would love to have you there. For any other questions on anything we did today, once I log off, YouTube keeps me connected for a couple of minutes. So I'll answer questions here. And then for anything else, you can always put a question under the video or email me and I will get back to you as reasonably as possible. I'm not like one of those big name companies that like never has time for anyone. So students will respond to emails and say, wow, you said you reply, but I didn't know you do. Yes, I actually do. Of course, when I have time, sometimes I'm busy, like tomorrow. But yeah, so any other questions you have, let me know. The link to join is layerforsci.com/join, and have a wonderful, wonderful evening. Max, any questions on that? It's all on the link, layerforsci.com/join. Have a wonderful evening.